So
okay, it's true.
Probably another scary season there.
Okay, I think we better get started.
Okay.
Ronit, do you want to do the introduction?
Yes. So I'm very excited to welcome Dimitri Sverjensky to our Institute seminar. Dimitri is a professor at Johns Hopkins University in Maryland. He did his PhD in geology at Yale, where he studied the origin of base metal sulfide ore deposits in sedimentary rocks and the origin of fluids in sedimentary basins. Currently, he's working on understanding fluids in the deep earth and how fluids affect the evolution of planets. He specializes in thermodynamic modeling of experimental studies, such as mine and others, as well as analysis to study and better understand the evolution of the Earth. And his talk today is going to be on how Earth's surface is habitable by permission of the deep Earth. Please.
Thank you very much, Ranit. It's a great pleasure to be able to give this seminar and to communicate with my colleagues who are able to attend. The title of this talk really comes from a colleague of mine, Craig Manning at UCLA, who I think made this statement up, that Earth's life at the surface of the Earth is by permission of the deep Earth. And it really struck me as something that we should think about, because often in our daily lives, we don't think much about the deep Earth, and perhaps we take it for granted a bit too much. But over geologic time, there's no question that the deep Earth has played an incredibly important role in keeping our wonderful Earth habitable. The most dramatic manifestation of this, of course, would be volcanic eruptions. And in the United States, the most recent dramatic eruption on the continental United States was Mount St. Helens in 1980. And obviously you can see vast amounts of gases pouring out of this volcano that have some imprint on them from the deep Earth. And we suspect this is the case because present-day volcanoes and also volcanic emissions, as far as we can tell, for most of the history of the planet, have really emitted very benign gases such as CO2, SO2, N2, and water, as a gross generalization, rather than the possible nasty equivalent reducing gases, methane, H2S, ammonia, and H2. So as a generalization, we have these rather benign gases that are keeping our planet habitable. And they are really, instead of what could be emitted, which would be a very different set of life forms on the surface of the Earth. So there's two very different states of oxidation that we can think about here. And the big question is why this is the case. This cartoon is actually after my colleague Craig Manning at UCLA, appeared some years ago. So here's our arc volcano emitting gases. And if we progress down into the deeper crust, there's a complex situation whereby magmas are stored and reservoirs are refilled and contamination can happen and lots of processes can take place. Further down, we get ultimately into the arc magma source region. And this region is thought to be in the area of the upper mantle that is potentially influenced by subducting plates. So in the asthenospheric mantle here, where the mantle flow direction is shown in this cartoon like that, we have a subducting plate coming down, and in this diagram, in this cartoon, there's a lot of focus on carbon. And carbon can presumably come off the slab in slab fluids of some sort. This is what's been suggested for many, many decades. And it's also been suggested that these fluids influence the oxidation state of the arc magma source because in fact they may be triggering melting in the mantle. And ultimately that imprint of oxidation is something that is reflected in emission of volcanic gases. So the question for now is, what kinds of fluids are these? And I'm really going to focus on two pressure or depth regimes in this talk. Shown here, we might talk about depths of 2 to 4, corresponding to 2 to 4 GPa, or 20 to 40 kilobars pressure, let's say 60 to 120 kilometers depth, what we might call sub-arc depths. So that's going to be my lower pressure range I'm going to talk about, and pay particular attention to what is the oxidation state of these fluids that comes off slabs. But I'm also going to talk towards the end of the presentation about much deeper fluids lower down in the subduction process, past this depth corresponding to the subarc depths, and how potentially they may also be in some way connected to the near surface environment. So the volcanic gases that we can see from volcanoes have been linked in their oxidation state to the rocks that can be studied, gathered at the surface of the earth and studied. And these are some results for basaltic volcanic rocks collected and summarized by Evans et al. 2012. And on the x-axis is simply the magnesium concentration of the olivine in the basalt. So very magnesium rich olivines, obviously, but with quite a range of magnesium concentration. On the y-axis is this parameter delta QFM that is a favorite parameter of petrologists for expressing the oxidation state of rocks. It can also be used to express the oxidation state of fluids. And what you can see here is that mid-ocean ridge basalts, or morbs, at the spreading centers are thought to have values of this delta QFM parameter a little bit above 0. Those are the black closed symbols. Whereas oceanic islands, represented by these open squares and triangles, have oxidation states significantly greater than perhaps between 1 and 2, at least. And the arc volcanics, high potassium are the closed circles, lower potassium are the open circles, cover a broad range going up to much higher values of delta QFM. And it's long been suspected that this high value of delta QFM for arc volcanics is in some way connected to fluids coming off subducting plates. So this just summarizes arc volcanics tend to be oxidizing. And the questions that follow are subduction zone fluids responsible? How could highly oxidizing fluids be generated at upper mantle conditions? And if they are generated, can they transport this oxidizing signature from the plate into the mantle wedge? And if so, which chemical elements are really transporting the oxidized signature? Because although we talk about partial pressures of oxygen here, log FO2 values, the absolute values are very low. FO2, the partial pressure of oxygen or fugacity of oxygen, is of the order of 10 to the minus 20 to 10 to the minus 30. So it's not oxygen that carries the signature. It has to be something with variable oxidation state. And the only elements with sufficiently high abundances are iron, carbon, or sulfur. So first of all, I want to take a look at what are these fluids like as we look deeper into the upper mantle. For many decades, we had a traditional CHO fluid model consisting of molecular gases dissolved in a fluid phase that had a very simple composition, such as the one shown here, CO2, methane, H2, H2O, and perhaps some other hydrocarbons. And the assumptions here were that there were no other solutes, no silicon, no magnesium, no other rock-forming elements, and no ions, no charged species, and therefore no direct link to silicate rocks that the fluids are actually hosted by, except through some mysterious connection with the oxidation state and the FO2. Now, this fluid model was really called into question by a number of lines of evidence, particularly fluid inclusion evidence from very deep rocks, including diamonds, that came from some of the very earliest studies were carried out by Oded Novon at your institution. And subsequently, these pioneering experiments by Ronit Kessel, which everything I'm going to talk about today depends on. If you don't understand that by the end of the talk, I'll be very disappointed. So here's an example. Here's a potassium-free eclogite, synthetic eclogite at 5 GPa, and the molality of silicon is plotted here. So that's the number of moles of silicon per kilogram of H2O in the fluid. So this is a subsolidus fluid, and the dashed line here simply connects the points at different temperatures. And you can see that up here we've got of the order of 11 mole silica in the fluid. Now, there are no fluids anything like that at the surface of the Earth. These are really remarkable aqueous fluids. They still have about 50% water in them in this case, but they have a lot of other dissolved constituents. So clearly, this is not something that we could get an understanding of with a CHO type fluid model. Another line of evidence came from work done early in the Deep Carbon Observatory when I first visited Lyon and started collaborating with Isabelle Daniel here and her postdoc at the time, Sebastian Farc. They were doing experiments putting a calcite crystal in the diamond anvil cell. So here's the boundary of the cell. This is 20 microns. It's a small calcite crystal at 1.7 GPa and 400 degrees centigrade. As they went up in pressure, I should say, a beautiful aragonite crystal formed by 3 GPa. And then at higher pressures, you can see it starting to get rounded edges and dissolving and becomes a stubby little crystal by 7 GPa. And the really important feature of this experiment are the Raman spectra taken at the temperature and pressure of interest, which document the emergence of bicarbonate and carbonate ions in the fluid. So here we have unambiguous evidence for ionic speciation in these high pressure fluids at 400 degrees centigrade. Another great result that came out in the Deep Carbon Observatory was a paper by Pan and Gali in 2016 using ab initio molecular dynamics at 1,000 degrees Kelvin, 727 centigrade, and about 110 kilobars. They found that a sodium carbonate or bicarbonate fluid contained not only a lot of ions, bicarbonate ions, carbonate ions, and sodium ions, but also complexes of sodium with bicarbonate and sodium with carbonate, and a whole series of these complexes. So this gives us an idea that these fluids could potentially be quite complicated with regard to the species that are actually in the fluid. And that's important in terms of solubilities of minerals, solubilities of rocks, and mass transport of material by fluids passing through upper mantle rocks. Another major discovery in the Pan and Gali paper is that instead of the CO2 molecule in a high pressure fluid like this, there was instead H2CO3. I'd like to say that H2CO3 is the molecule that geochemists forgot. We all know from ambient studies of CO2 dissolving in water that CO2 reacts with H2O and forms bicarbonate and carbonate. But the quantity of H2CO3 molecule at ambient conditions is just trivial. It's a tiny fraction of a percent, and so we ignore it. And that's fine. But instead, at high pressures, we're finding that H2CO3 is an important molecule. And this is not a trivial result. This is a very important result because we can think of H2CO3 as a complex of CO2 by water. And to my mind, this raises a lot of very fascinating and interesting issues. And I think it's going to change a lot of ideas about deep fluids. But for now, the important thing is that this traditional CHO fluid model is simply not tenable given what we know about experimental solubilities, experimental speciation of fluids at high pressures. And I haven't had time to look at and talk about this now, but there are innumerable petrologic studies documenting mantle metasomatism, that at times mysterious process that no doubt transforms rocks, leaving at times only isotopic or trace element evidence, but at other times major mineralogical changes as well. So about 6 years ago, I started publishing a new type of model where we built on the old regime of aqueous geochemistry that traditionally was only able to go to 5 kilobars or 0.5 of a GPa with regard to quantitative thermodynamic characterizations of aqueous ions. And this whole regime, embodied in the computer code Supercrit 92, a very widely used code all around the world, was developed by Helgeson and co-workers at UC Berkeley and refined and developed as a predictive tool for many different aqueous species of all kinds by Everett Schock in his PhD thesis in the late 1980s, working with Helgeson at Berkeley. It's been possible because of the new data in Lyon and other data to be able to extend this modeling capability up to 6 GPa. In fact, at the ab initio conditions, even up to 10 GPa, it would be possible. And this has led to a deep earth water model that is based on these various details, particularly the Zhang and Duan equation of state for water at high pressures, the revised Helgeson, Kirk and Flowers HKF equations that were built by Schock and colleagues that I have modified to be able to go to high pressure using the Raman data that Isabel Danielle and her colleagues have measured, and then thermodynamic properties of gases and minerals that are consistent with this. Recently, my former student Fang Wang and I have published a revised, expanded model where the big challenge here is to use all this remarkable experimental solubility data that Ronit Kessel's group has measured to calibrate potential new complexes to try to account for the high solubilities. At the same time, we used activity coefficient models for ions and neutral species, including provision for very high CO2 content, an activity model for water, so that we could have activities of water less than 1, and explicit provision for hydration of aqueous species, so that silica is now written as SiOH4, magnesium as MgOH2, that's just one of the many magnesium complexes, and of course this new complex H2CO3 and many other complexes. The importance of the provision for hydration, like with SiOH4, is that the solubility of silica in equilibrium with silicate minerals, for example, coesite, the high pressure form of silica, becomes a function of the activity of water. So that's something that's been experimentally studied in great detail by Manning and co-workers, and that's something we can now model explicitly. An overview of the current chemical capabilities is summarized here. We can deal with all the major elements shown here, not all of which are as well calibrated as others. And in fact, still particularly carbon and chloride, which are of great interest, need extensive calibration. At the moment, chloride is based on all the work done at low pressures and temperatures for crustal hydrothermal systems and extrapolated to high pressure. With minor and trace elements, we can construct models for these species. And most recently, in the last year, I've been working with my former postdoc Simon Matthews on zirconium in fluids and titanium in fluids. And I think another possible trace element one could look at would be strontium. That should be possible very soon. All of these species form cations, anions, and complexes. For example, complexes with carbonate, with formate, and that's an organic acid anion. Calcium silicate complexes, other kinds of silicate complexes, and formate complexes, so that the speciation of the fluids, the kinds of complexes in the fluids, is really a key to being able to model the chemistry and the water rock interactions involving these fluids. And this is really where the most need for new experimental data lies. We now have already a fantastic base of solubilities of rock types, but what we really need is new experimental speciation data for high pressure fluids, and that's going to be a very difficult task to approach. Experimentally, it could be done, but also I think computationally with ab initio methods that could make a big contribution as well. So basically, we have at the moment our major element speciation is calibrated with this experimental solubilities of upper mantle rocks from a very wide range of papers by Ronit Kessel's group. And these cover basically 4 different rock types: potassium-free, potassium-bearing eclogite, potassium-free, and potassium-bearing peridotite. And I mention this explicitly because each of these 4 rock types in equilibrium with a fluid gives a different fluid chemistry. And the different fluid chemistries result in different solubilities and different potential speciation. So we take advantage of this range of fluid chemistries to construct a fluid speciation that is consistent at a given temperature and pressure with all of the different 4 different fluids from the 4 different rock types. I want to emphasize again that these are the only experimental data at these conditions, so it's really invaluable. We're just now starting to look at some lower pressure data for pelitic systems measured by Jörg Hermann and colleagues. So essentially, this gives us equilibrium constants that we can extrapolate over wide ranges of temperature and pressure using the Dieu model and equations of state for each complex. And I've spent a lot of time describing all that in my class this semester. So if you want to know any more details about that, Amit Meltzer can now explain that to you. We also have an activity coefficient model, as I mentioned, and we use mass action, mass balance, and charge balance equations together to be able to calculate models of aqueous speciation and solubility using the code EQ3 that has been modified for high pressures and temperatures, and to do chemical mass transfer calculations using the code EQ6, where we can answer the question, what happens when a fluid encounters a new rock type that it is not in equilibrium with? What kinds of water rock interactions take place? So here we're able to model now irreversible chemical mass transfer between fluids and rocks under upper mantle conditions. So looking back at our cartoon, the traditional approach has been confined to studying volcanic rocks themselves, from which an enormous amount of information has been gathered, as well, of course, as studying the intrusive equivalents exposed from depths in the crust and the upper mantle. So the traditional approach has been to go backwards from the surface exposure of rocks and infer processes involved with the subducting slab. In addition, there's been modeling of what takes place in the subducting slab by a wide variety of workers, particularly Hacker and co-workers. What we can now do with the deep earth water model and the codes, modeling codes for chemical mass transfer, is to be able to go forwards and ask the question, what do these fluids really look like, and what predictions can we make when they leave the slab and encounter the asthenospheric mantle? So we can go in a forward sense back up towards here that complements the traditional approach going back down with depth, inferring things from the surface. So as I mentioned at the beginning, I want to focus on two depth zones. The first depth zone would be 2 to 4 GPa. At subarc depths, that would be these kinds of depths here. The second depth zone I want to talk about is much greater depths at 4 to 6 GPa, below the depth where serpentine breaks down, and to look at the possible connections between fluids here and ultimately the surface environment. So at the shallower depth, 2 to 4 GPa, how are these highly oxidizing fluids generated at shallow upper mantle conditions that people have suggested for decades, going back to Ian Carmichael a long time ago? The long and short of it is that in a collaboration with Baptiste Debray, who's a petrologist who studied serpentinite breakdown reactions, that we think that that serpentine plus magnetite plus H2 go to olivine plus orthopyroxene at high pressures and temperatures is something that results in very oxidizing fluids. And Baptiste has documented in some detail the progressive breakdown of magnetite in a series of rocks in this process. The most extraordinary location where this can be studied, and it's been studied for decades, originally by Volkmar Tromsdorf from Switzerland, more recently by Alberto Padron Navata, who is in Montpellier, and his Spanish colleagues. This is the Serra de la Maris serpentinite in the far south of Spain. And this is an outcrop that shows you the green color here is the serpentinite, and then it passes into a narrow transition zone here, represented by this orange zone here, where we have a change in the kind of olivine. We have chlorite appearing, coming in here, going from right to left. We have orthopyroxene appearing, and then finally we have the disappearance of antigerite, the complete breakdown of serpentine here along this dark purple line. And this dark rock here represents the chlorite Harzbergite rock that is the peridotite result of antigerite breakdown. So this outcrop has been studied in great detail, not without some controversy by a variety of workers. But the interpretation that I'm going to accept is the one presented by Padron Navata et al. In 2011, which is that this is a continuous breakdown zone of antigerite. The interpretation places this in the zone of subduction here, where the wedge serpentinite coming down in the mantle wedge that's been altered by fluids from the slab at lower temperatures finally breaks down along this antigerite line, antigerite outline here, and the Harzbergite is generated. So this can be represented simplistic by antigerite serpentinite, transitional assemblage, and chlorite Harzbergite. Baptiste Debray has documented that magnetite decreases throughout this transformation. And you might expect if magnetite is being destroyed, that the ferric ion and the magnetite Magnetite, of course, has both ferrous ion and ferric ion. The ferric ion has to go somewhere. So the only place it can go here is into forming some hematite, and also to get reduced as ferrous ion into the olivine and the Habitable. So in Debray et al. 2015, it was documented for the first time that some high pressure, high temperature hematite appears to have formed at the time this Habitable was formed. So the details of this model are not particularly important right now, but essentially what I did was heat a fluid equilibrated with antigrite serpentinite at 630 degrees centigrade and 2 GPa, heat it from 630 to 660, going through the antigrite breakdown at 653 degrees C at this pressure, and follow the water-rock interactions. So part of the mineralogical transformations are shown on this slide. So the amount of moles of mineral here, of magnetite, that get destroyed, the moles of hematite that appear, and the moles of antigrite that get gradually destroyed and then all of a sudden disappear completely here. So we're heating along here on this x-axis with reaction progress. The temperature is going from 630 up to 660 at this point, and at 653, the antigrite breaks down and disappears. So xi here is the reaction progress variable. As a function of the same reaction progress variable shown here, we have the magnetite again, the hematite again, I've repeated, and we've got olivine being continuously formed, precipitated, recrystallized from the older rock and forming new olivine from the transformation of the antigrite all the way through up to the end. We also find chlorite appears, just like in the rocks in the Serra de la Marez, and then orthopyroxene appears. So the types of rock, types of minerals and the rock we end up with match very well, both in sequence and relative abundances, to the rocks in the Serra de la Marez. We end up with a olivine orthopyroxene rock with some chlorite and a small amount of magnetite and a tiny amount of tremolite. So the same model continuously follows the temperature, the FO2, the mineralogical transformations I've just shown you, but also all the fluid chemistry, which I'll talk about later. And the important thing here is that temperature is going from 630 degrees here, temperature axis obviously on the right, up to 660 degrees here. And the log FO2 skyrockets up here to very high values. So it's about minus 9.5 at the finish. And at 660 degrees, the QFM index is that value there, which is about minus 16. So we're about 7 units from minus 16 to minus 9.5. We're about 7 units above QFM. It's a colossal change in FO2. This is driven by the breakdown of magnetite and the fact that the ferric ion in the magnetite has essentially nowhere to go. It forms a little bit of hematite, but most of it has to go into olivine. When it goes into olivine, it has to go in as Fe2+, not Fe3+. And that produces a very oxidizing result because the ion is going from Fe2+ to Fe3+ to Fe2+. It's the reverse of the original serpentinization, which is a very reducing reaction and produces hydrogen. So we can think of this reaction as consuming hydrogen from water and reducing ferric ion to ferrous ion. Overall, this model agrees with the observed mineral assemblages in some detail, and the deserpentinization or the breakdown of the antigrite, the serpentine, leads to a dramatic increase of the FO2. So here is a mechanism, at least one mechanism, for generating highly oxidizing fluids as part of the subduction process. And one could argue that since serpentinization is ubiquitous in subduction zones, and it's also true that at great enough depth and high enough temperature, serpentine has to break down eventually, so that one could argue that highly oxidizing fluids might be quite common in subduction zones. However, the most interesting question really is what happens to these fluids? Can they survive, or will the rocks surrounding them simply alter this highly oxidizing signature? And this is something we can now address with irreversible chemical mass transfer models. And we need to look at whether sulfur or iron or carbon can carry this oxidizing signature. So in our 2017 paper, I carried out calculations with no iron sulfide present. Pyrrhotite was the iron sulfide I used. So with no iron sulfide, we had this huge range going up here to minus 9.5. But if the serpentinite happens to contain various amounts of iron sulfide, pyrrhotite, for example, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1 moles of pyrrhotite per kilogram of reacting water, then you can see that with the highest amount of pyrrhotite, this dashed blue curve, the signal is substantially damped out. Of course, iron sulfides and other sulfides might be common in serpentinites, and so this could easily damp out the oxidizing signal in many cases. So let's look now at whether iron could carry an oxidizing signature. This is the fluid chemistry that corresponds to the model I just showed you, where the antigerite was breaking down up near log xi of 0. So with increasing temperature, you can see that the fluid chemistry doesn't change very much. The main species of magnesium here is MgOH2. In this model, the main species of CO2 is CO2. SiOH4, sodium chloride, an aluminosilicate complex that here is predicted using the deep earth water model, but was originally calibrated with the eclogite and peridotite solubility experiments I referred to earlier. Similarly for the calcium silicate complex and the iron silicate complex. So the predominant form of dissolved iron is predicted to be an Fe2+ silicate complex that has a charge of +1 here. There's no significant ferric iron predicted at these temperatures and pressures, which is a very general result for aqueous fluids. The lower oxidation state always predominates at high temperatures. So iron is simply too low in abundance here, millimolar levels, to be able to transport the oxidizing signature. But you notice that carbon at 1 mole here is certainly abundant, and at a level of 1 mole per kilogram of water, there's a substantial amount of carbon in the fluid. So this strongly suggests that carbon in fluids coming off subducting slabs in this little cartoon might be able to transport an oxidizing signature into the mantle wedge. And the water rock interactions that take place in the asthenospheric mantle can be modeled, as I'll show you next. The actual melting process, we haven't modeled yet. So here are predictions. These are all part of a single model, but I'm showing you the minerals produced here and destroyed. The temperature is constant here. The dissolved aqueous chemistry is fairly constant. And what we're looking at here is this very dilute fluid from the breakdown of antigerite that contains 1 mole CO2, but it's really otherwise a pretty dilute fluid. There's a lot less sodium and silica and aluminum and calcium and iron in this fluid. So how does this dilute fluid react with upper mantle lozolite at 2 GPa and at a temperature of 660 degrees centigrade, constant temperature. So olivine is destroyed, orthopyroxene is destroyed, some hematite forms, but then disappears and is overtaken by a very small amount of magnetite. And the final rock type has a lot of clinopyroxene, a fair amount of chlorite, and a lot of olivine. So it's really a clinopyroxene-rich rock with a lot of olivine in it. So it's a special kind of peridotite. Of interest to us here is that the FO2 initially at minus about log FO2 minus 9.5 plummets down to here about minus 13.5 or so, which is about 2 units or so above QFM at 660. So we go from an extremely oxidizing fluid down to about QFM plus 2 or so. And at the same time, we produce olivines which have magnesium numbers of about 82, that is to say 82% forsterite, 8% phthalate. So significantly more magnesium rich than standard upper mantle olivine. And broadly speaking, this artificial rock type that I produced is similar to a whole class of xenoliths that are found in alkaline igneous volcanic rocks in oceanic islands, as summarized in the Treatise of Geochemistry chapter by Graham Pearson and colleagues. So I was rather intrigued about that because it perhaps gives us some potential connection from subduction zones all the way to oceanic islands. So going back to our original little plot from Evans, we can see that if we have QFM plus 2, we are at least in the lower part of arc volcanics here, and possibly this is a way that we could produce an oxidizing signature from this process. So I think that carbon is the most likely element for oxidizing the convective upper mantle by fluids. And this could result in partial melting and eruption of gases ultimately that are the kinds we want that are benign to life. So perhaps life at the surface of the Earth is possible by permission of water rocket reactions at depth in the Earth. I now want to transition to greater depths. So we've looked at this kind of depth interval and this kind of trend here from subduction zones through up volcanic arcs, in this case on the continents. But we now like to look at, I'd like to look at depths that are much greater, depths that are of great interest to people in your institution. And one of the most remarkable things that has been extensively studied at the Hebrew University of Jerusalem is this whole issue of criticality. At relatively low pressures, depending on the bulk composition of the system, these cartoons, which I've modified after Herman in our 2006, show that we don't have a continuum between water and rock, unless we go to very high temperatures where we get a supercritical fluid. Instead, the onset of melting here marks the transition from a fluid in this region under subsolidus conditions that gradually becomes more rich in solute. And finally, at melting, we have a fluid migrating along this curve and a melt composition migrating along this curve. And at some particular temperature above the solvus, we get a supercritical fluid. But if we go to great enough pressures, it's been amply demonstrated experimentally that we in fact have a continuous solubility curve from H2O-rich fluid to silicate-rich fluid. So technically these look like melts in their bulk chemistry because they have low water contents. And these look like water because they have low silicate contents. But in fact, we should, from a physical chemical standpoint, call this whole region fluid because it's a continuous solubility curve. in polytic systems, Hermann et al. Have shown that this occurs at possibly at pressures as low as 3 to 4 GPa. But it's a strong function of the bulk composition. So from a modeling standpoint, which is where I'm coming from, the question is, how far can we go with our models? We know that we're coming from a very water-rich realm. That's the traditional aqueous geochemical modeling realm. And we can extend that with increasing solute contents along this curve to some point. But we don't quite know how far along we can go yet. So here's one indication of how far we can go. This is a subsolidus fluid that I showed you earlier with very high silica concentrations. And I've put the weight percentages here for people who like to think in terms of weight percents, whereas in aqueous geochemistry, we're always using molalities because that's the most convenient for modeling aqueous fluids. And you can see that the red curve here, which is our best fit to the experimental data from Kessel et al. 2005, is a smooth curve here. And based on that, we can make predictions using the complexes and the equations of state. We can extend things from 5 GPa to 6 GPa. And we have here experimental data published just last year by Elazar et al., also from your institution, where we're now predicting what the red curve is a prediction based on all the modeling from 4 to 5 GPa I talked about previously. And here we can see that even with the supersolvus fluid, we're going to quite low water contents, 25 weight percent water in this model. So this is a fluid that looks something like a melt, but technically it's a supersolvus fluid. It's a supercritical fluid, and I like to use this adjective supersolvus to emphasize that we're above the solvus. So perhaps under these conditions, we can go to 1100 degrees C at 6 GPa, and water contents may be around in the mid-20s. Whether we can go further remains to be seen. And that's the topic of a project that Mark Giosso and I have been involved in for several years now, to be able to go continuously from water to silicate liquid or fluid containing very little water. We can now make predictions. Here's a prediction for the molality of carbon in equilibrium with diamond, garnet, clinopyroxene, and coesite in a potassium-bearing eclogite. And you can see that the solubility of carbon is predicted to increase extraordinarily with very high values up here. The speciation that's predicted in this model is H2CO3 formate, which is this organic acid anion, and CO2 as well as just a minor species here. And most of the carbon is actually complexed with magnesium and with other chemical elements that involve formate and bicarbonate and carbonate. So this is a new way to look at these fluids. I would like to emphasize there's a lot of uncertainty about the speciation in these models, and that's really the frontier where we need new experimental data to try and figure out what are the actual species in these fluids and what are the activity concentration relationships, particularly for this species H2CO3 and CO2. In any case, regardless of the actual values, it would appear that there are substantial quantities of molecules like H2CO3 and formate. The oxidation state of carbon in H2CO3, of course, is carbon +4, but in formate, it's carbon +2. So we can write an equilibrium here between oxidized carbon, reduced carbon, H+, and O2. And we can also write an equilibrium between formate, H2CO3, and carbon in the form of diamond. So these two equilibria together fix the pH and the log FO2. And the reason is simply that there's a lot of carbon dissolved in the fluid. In the model, we have molar levels of H2CO3, molar levels of formate. So the chemical potentials of those species are essentially fixed. This is an observation that Helgeson made way back in 1970 in crustal hydrothermal oil-forming systems. Once the chemical potentials of certain aqueous species are high enough, they can buffer the fluid. So the fluid is internally buffered. And here we're buffering the pH with this reaction because of equilibrium with diamond. And in combination with this reaction, when the H plus formate and H2CO3 are fixed, we're buffering the FO2. So at 1100 degrees C and 6 GPa, which was experimentally studied by Elazar et al., and the log FO2 was actually measured, we have an FO2 that is predicted to be QFM minus 2.7 in our model, which is very close to the measured value. So I think that a major conclusion from our preliminary studies of these very high pressure fluids is that the high solute contents with these complexes could actually control the FO2 in the mantle during diamond formation and mantle metasomatism. In other words, these fluids are the boss during water-rock interactions. They can impose things onto the ambient mantle. Certainly there will be changes mineralogically and changes with regard to trace elements and isotopes, but in terms of FO2 and pH, mass transfer calculations indicate that very little changes, in contrast to the example I showed you at the lower pressures previously. This is something of a theme that I think was originally suggested by Wood et al. 1990, and in some recent papers, Kaseva and Wood have amplified this topic. For example, in a project I have with Sami Mikhail at St. Andrews in Scotland and his student Michele Rinaldi, we've been doing a lot of metasomatic models at 5 GPa and 1000 degrees C, where a mafic eclogetic fluid reacts with leusolite and forms garnet clinoperoxenite. So we get a whole new rock type formed. Clinopyroxene is incredibly easy to form in these metasomatic models. But importantly, the FO2 is essentially unchanged and the pH is unchanged. A similar approach was taken in the recently published paper by Wang and Sverjensky 2020, where we modeled a specific diamond formation event in the Panda kimberlite diamond mines, where we had a carbonatitic fluid chemistry altering Harzbergite at 4.5 GPa and 950 degrees C. And it was a more complicated model. We also had mixing with a saline fluid. But what was interesting was that we did get an olivine and garnet-rich rock. The FO2 was changed a bit because of the mixing with the saline fluid, but we had iron enrichment in the olivine and calcium enrichment in the garnet. And I think if we could include calcium as a component in olivine, which I think is possible, I think that we might well find that there'd be calcium enrichment in the olivine as well. So I think there are people listening who'd be very interested in that. In fact, I'm now showing this picture from Yakov Weiss's recent paper because it stimulated a lot of thought on my part. I had never thought of this kind of grand scale of recycling before, but in Yakov's paper, he was particularly concerned with explaining the so-called high mu anomaly in the mantle that is a long-lived anomaly isotopically, and now revealed by trace elements as well, that has long been studied, but the origin of it here was attributed to water rock or fluid rock interactions or melt rock interactions between a carbonatitic type of composition of fluid and the subcratonic lithospheric mantle that resulted in break-off here, long-term storage, and then incorporation into an upwelling plume that resulted in volcanic rocks that bear this high mu signature. So this is something that, at least in this part of the realm, could be now modeled directly, I think. And it might be that this cartoon also applies possibly to other systems. For example, the alteration of the asthenospheric mantle by eclogitic fluids that I mentioned in the last slide here. We might wonder that if that is a process taking place in deep in subduction zones, how much of the lersilytic mantle or the asthenospheric mantle might be altered to clinopyroxene-rich rocks that also have some influence perhaps on the mid-ocean ridge and maybe on some of the oceanic islands. So this is a highly speculative result or suggestion, but I'd raise it as an interesting possibility that could be investigated. So in summary, we have subarc mantle fluids that appear to have the possibility of producing highly oxidizing fluids during serpentine breakdown, which can influence arc volcanics and the emission of benign gases. That's something I think that is on fairly solid ground now. And more speculatively, we have the issue of deeper mantle fluids with a very high solute content that can impose FO2 on the mantle, perhaps of different kinds, during diamond formation and mantle metasomatism. And it's possible that this could have influence on ocean island volcanics, maybe even on morb generation and the emission of gases of oxidation states that are appropriate for those rock types, and again, possibly for habitability. So I'm going to leave it at that. And I wish to acknowledge my colleagues, particularly in a variety of institutions, most especially today at the Hebrew University of Jerusalem. As I said, none of this modeling would have been possible without the experimental data produced there. And of course, the invaluable fluid inclusion data as well. Thank you very much. I'll be happy to answer any questions.
Thank you, Dimitri. Ronit, do you want to also handle the questions, or should I do this?
Okay. Anyone has any questions?
Hi, Lou.
Okay.
Hi, Oded.
Hi. Hi, Dimitri. Thanks for this very nice talk, and thanks for all the acknowledgements. I have a question regarding this serpentinization. Basically, you say when we go down, we will get an oxidized subduction slab, and then we can oxidize the mantle, and then at the surface or close to the surface, we serpentinized the morb, and we produce hydrogen, and this hydrogen can leak to the atmosphere and then getting lost from the atmosphere. So basically, is that when you do the grand mass balance, is that leakage of hydrogen what eventually turn the mantle more and more oxidized, or is that negligible and it's other processes, or it doesn't happen? What is the role of serpentinization and hydrogen loss?
That's a really fascinating topic. So in terms of possibly even influencing the great oxidation event at about 2.4 billion years ago, maybe. I haven't worked on that specifically, but I believe actually my colleague Everett Schock has some very interesting papers coming out on that topic very soon. The idea being, of course, that in the late Archean, or at least in the Archean, we had a lot of komatiites, and so the temperatures and the possible role of serpentinization might be different to after the Great Oxidation Event. And I think it's possible that if serpentinization and deserpentinization was even more important before the Great Oxidation Event, that maybe it could contribute to that. But really at this point, it's just a guess on my part.
Any more questions?
I have a follow-up question on what you just said, Dimitri. Thank you. First of all, thank you. It was I really enjoyed your talk.
Thank you.
So you said that it can contribute to the Great Oxidation Event, but I mean it won't produce molecular oxygen.
Right.
At best, you can lower the the buffering capacity, right, of mantle rocks and gases and such. So you still need photosynthesis to do its work. Do I understand correctly?
Yeah, I think it's complicated because before the Great Oxidation Event in the late Archean, it's my belief there was more hydrogen in the atmosphere, molecular hydrogen, than there was molecular oxygen. And so, as far as I'm concerned, at that time in the late Archean, the surface environment of the Earth had redox reactions and weathering reactions that was dominated by H2 instead of O2. And so if you start to get rid of the H2, a lot of the near surface microbiology and the weathering processes are going to be different. So it's, I think, impossible to say what would happen without taking into account the microbiology.
Yeah, thank you.
More questions?
Actually, I have a question for Yakov.
Sure.
Okay, great. So with this cartoon, you're accounting for certain kinds of oceanic islands, right? But it's my impression that that's a subset of the total variety of oceanic islands. Oh,
Yeah,
I can't hear
you.
Now you can hear me?
Yes, very good.
Strange. With earphones,
Yes.
you cannot hear me, and without, you can.
Yeah.
This is specifically applied, or what we said in this specific paper is that it's applied for the high mu, but we also suggested that it may apply for the whole range between high mu and EM1. So the other things, EM2, is not probably related, but all the range of the low neodymium array between high mu and EM1, we suggest that it might be explained by this contribution of metasomatized, in this case, metasomatized lithosphere, but it can be also metasomatized mantle in general.
Yeah. So you were specifically addressing destruction of clinopyroxene, correct?
Not that I recall.
Oh, okay.
No, not at all.
Not that I recall, no.
No, not at all.
I thought in your metasomatic description you said that clinopyroxene was disappearing.
No.
No.
Okay, I must have misunderstood that then.
Okay.
More questions? Okay.
I have one comment. I would say that diamond formation is associated with a very special kind of Harzburgite in which they are very chrome rich. You said that you just now start to look at chromium, but this may be an interesting thing to see if you can get any insight for the chrome budget during metasomatism, and maybe attack this problem of high chromium Harzburgite from a different point of view. Normally, people relate it to reaction of chromium spinels, but it's an interesting thing to check when you can model chromium.
That's something I have a student who's going to try to do that. We have a little paper published already on the aqueous speciation of chromium, but we have yet to apply this to chromium in the garnets. And when we can do that, we could attack that problem that you're talking about, because you're absolutely right. It's a fascinating problem as to why we have these high chromium, very low calcium garnets. We can produce very low calcium garnets in our models of the ones I referred to at the end of the talk, where we have a mafic eclogetic fluid reacting with lozolitic mantle or Harzburgitic mantle. We eventually produce extremely magnesium-rich garnets with very low calcium. So I think that's going to be easy to solve. Whether the chromium goes along with that or not remains to be seen.
Okay.
Okay. So thank you very much, Dimitri, for a very interesting talk.
You're most welcome. Thank you for inviting me.
Sure.
Thank
Our
you.
pleasure. Thank you.
Have a great day.
Okay, you too.
Stay healthy.
Okay.
Cheers.
Bye.
Bye.
Bye-bye.
Bye.